Hi, welcome to the Calculus 3 lecture series. And we are in the unit Vector Calculus and lecture number 9. This is our second video talk about the surface integrals here. Our first video for the lecture number 9, we talk about how to do the surface integral if you have a scalar field, or we call it a scalar field. It's like a real value function like fx, y, z functions. And then we say, how do we do that? And then for this videos here, we're going to go over is how about if you have a vector field, and then how do we do the surface integrals here? Okay, so let's go ahead and start. Let's go to our worksheets and the lecture notes and continue our lecture notes here. All right, so so here, so the first things here, let's take a look at our definitions here. We have a new definitions here. So we say the flux here. So what is a flux here? So if we say that F here, the vector field is a continuous vector field right now, and whose domain is including an oriented surface S here, then the flux, so if you try to do the surface integration of this vector field, so the physics application for that, we say, hey, this is we defined as flux. And then how do we do that is will be the vector field and the dot product, the normal vectors here. And so what is the normal vectors here? So the normal vector is very similar, just like we say you have the parameterizations, right? So for the u and the v's here. So this is my parameterization vectors, right? So then you have a partial u and you have a partial v's, right? So we know when we cross product two vector field, what do we produce? We produce a perpendicular vector. So that's what is this normal vectors about. And then we say the S here is oriented fields here. So when we applied this, we think this is, well, we call it a positive orientations here. So when we talk about the positive orientation, that means when you do these vectors here, so your normal vectors go outward. Okay, so it's similar like when we did the line integrals. So we said if a curve is a positive orientation, so what's that mean? That means the curve travel the counterclockwise, right? So in here in the surface here, we say it's the outward. That means see here, this is the normal vector, you go outward. So it's similar like what we did. So, okay, so the next thing here, this is a very importance, like it's very handy, I should say, very handy things here. So they have two special cases here for the surface integrals here. So first ones here, we say, hey, if you can parameterize your surfaces here, then you can just do RU, RVs, right? Because RU cross RV is what? It's a normal vector. And then the second one, this one is really pretty, it's become very handy. So if you say, hey, if your function z is a graph of the function gxy, then you can just change the surface integration to this formulas here. It's a negative p and rho g, rho x, rho g, rho y. And we're going to do some example to show you this one's really become pretty handy when you try to do the surface integration for the vector field. Okay, so now let's take a look at these examples here. Okay, so this example is showing you here. So S is a part of the parabolic cylinder, all right? So Z is equal to 1 minus x squared above the squares here. So F is the vector fields here. Then they say, hey, try to find this vector field, try to find the surface integration for this vector fields here, right? So here, this is the surface area. This is the surface I'm trying to integrating over, all right? Okay. All right, so let's try to do in two ways here. So the first way is here, let's try to parameterize it. Okay, so let's see how can I parameterize, it. Okay, so here this is a z equal to the 1 minus x squared. Well, so let's see here. So we said when we do those type of problem, parameterization is the hardest one. Okay, so let's take a look at method number 1 here. Okay, so let's say here, I would say x equal to what? Let's say x equal to u, okay? Y, and y equal to v. This one turns out pretty good. So what is z here is y minus what? U squared. The reason why I choose these ones here is also, this is pretty good is because I know here, right? So this is in the boundary. So the region D is here. You see that? All right. So that's why we can say the U is from 0 to 1 and the V is from 0 to 1. That will make our integration a lot easier. So like we did before, so this is my parametric vectors, right? RUV. So this is the U, V, 1 minus U squared. So take a partial U, this will be 1, 0, negative 2U, correct? Partial V will be what? 0, 1, 0, right? So we should be very familiar right now how to do this cross product. So RU cross product V, and I'm not rewrite it. So basically you will have 2U to the I components plus K. Okay, so this is the RU, RVs here. So this one's here. This is a 2U, 0, and 1 here. Okay, so now let's take a look at it. Now I substitute to the function, the first function here, right? I substitute here is f dot RU cross RVs here, right? Okay, so what is my f here? Okay, so now the f here, f of this vector field x, y, z is equal to what? 2y, so it's 2v, right? 3z, so what is 3z? So it's 3, 1 minus u squared, right? And 4x, so what is 4x? Is 4u, correct? Okay, so now I'm going to do the f of the RUV, right? Dot product RU cross RV. Okay, so that means I have this is 2v, 3, the 1 minus u squared, 4u, dot product 2u, 0, and 1. So far, so good. So when you dot product, you just times it. So it turns out to be pretty easy. So this is 4uv. This is a complicated term, disappears, 0, and the plus 4u. That's pretty good. Okay, so now you can see now your integrations here, the integration over this surface, right? F dot ds, this vector field over this surface. It's just like we did before. For the scalar field, you can change to a 2 variables here, right? So what is the 2 variable in here? We have 4uv plus 4u. Then you can do dv du or du dv. So if I say the dv du, and then also in here we have a very good bond, right? So we'll make our integration pretty easy. So this will be 0, 1, 0, 1. So what do you have here? So you have this 3 here. It's good. Okay. So now let's say that, hey, we can do 2 ways because in here, you know, the surface is a scalar function. You can say z is equal to 1 minus x squared. So z is a function of x, y, z here. So let's take a look. How do I do this one here, right? Okay, so let's back to what we here, all right? So I know the z is equal to 1 minus x squared, right? So z is equal to 1 minus x squared. That means g xy, right, is equal to the 1 minus x squared. And then the f of x is here. So I know the p is equal to what? P will be equal to 2y right? So P is equal to 2y, and then the Q is what? So P is 2y, and the Q will be, let me see here, will be 3z's here, right? Okay, so in here, so P, we said P, okay, so P is 2y, then Q is 3z, and then what is my R? R is 4x here, right? Because here my f of x, y, z is equal to 2yi plus 3zj and plus 4xk, right? So this is the PQR. Okay, so now this is a G, so we do the partial. Gx here is what? Negative 2x from here. Then the G partial y, there's no y, so it's zeros here. Okay, so now I plug in this surface integration of this vector into the second equations, right? So the second equations here is yx here, right? So take a look here. So this is the second equation, is negative p, rho g, rho x, negative q, rho g, rho y, then r, okay? So now the p, negative p is here, p is 2y, so the negative p, it will be what? Negative 2y times rho g, rho x times negative 2x here, minus negative q's, right? So minus q, so the q's here is what is 3z's, right? So 3z, so okay, so minus 3z, and then rho q, so the minus rho g, rho y, so it's 0, rho g, rho y is 0, then plus r, r is what? R is 4x here, right? R is 4x here. Then you do dy dx or dx dy, doesn't matter, dy dx is here. So now my here, this is 0, 1, y is 0, 1, see here, okay? So now you here, you say 0, 1, 0, 1. So this will be 4xy. This term disappears, right? It's plus 0, plus 4x here, okay? So in here, that's why this is 4x here, right? Okay, good. So that's why you simplified to the dy dx. You simplify a lot, right? So to become the typical calculus 2 integrations for xy. So what is the answer here? You get the same answer. It's 3 as you use the parallelizations, okay? So either way, you will get the same answers. And sometimes these ones here will make the, make the calculations somehow, sometimes it's easier, right? Of course, it depends on what is your functions defined, right? Okay, so now let's take a look at some other examples here. And these ones here, I want to evaluate the surface integration of this vector field. And the S is the top of the half of the sphere, right? So x squared plus y squared plus z squared is 36. And my vector field is zk here. All right, so now let's take a look here. So this is a sphere. So I need to parametrize it, okay? So in order to parametrize it, I know this is so this is the rho squares, right? So this R is a constant. So I know the spherical coordinates, I know the rho is 6. And then based on these ones here, then my theta here is from 0 to where? To 2 pi. Because this is the top one, so what is my phi here? Phi here is from 0 to what? Pi over 2 here. So then obviously then this parameterization would be pretty easy because I use the knowledge we learned from the sphericals, right? So we can say x equal to the 6 sine phi and cosine theta. Then y is equal to what? Y is equal to the 6 sine phi and sine theta, right? So we are kind of using the knowledge we learned from the spherical coordinates. And then the z, we can say, hey, the z is what? Z is 6 cosine what? Cosine phi here. So see here, so these ones here, I transfer to the parameterization. So what is my parameterizations right now? Is phi and the theta, right? So it's the theta and the phi, so or phi and the theta, doesn't matter, right? Okay, so we say it's a phi and the theta. So right now I transfer this 3 variable to the 2 variables. So I do the parameterizations. All right, so now you do the same routines here, right? So these ones here will just be x, y, z's here. So if you want, you can write this is 6 sine phi cosine theta. And then this is 6 sine phi sine theta. And then this is 6 cosine phi, right? Okay, so now let's do the same thing. So after this, so I say partial for phi. Okay, partial for phi, I will have this is 6 cosine phi sine theta, cosine theta, and 6 cosine phi sine theta, and negative 6 sine phi, right? So it's kind of a little bit tedious, but that's okay. Then the partial for the theta will be negative 6 sine phi sine theta, so this will be 6 sine phi cosine theta. Then the last one doesn't have theta, so it's 0. All right, so now you can do this, and then you do the r phi cross r theta. So you use the same definitions we did. So I already got this one down here, so you can verify it to see if you can get the same thing. So I will have the sine square phi cosine theta. This is my I components. Then I have a sine square phi. Okay, sine theta. This is my J components. And then I have a sine phi and a cosine phi K components, right? Okay, so this is my vector. I should use the vector symbols here. Okay, so now your F here, your F is what? Oh, F is pretty easy, it's Z's, right? So F dot R phi cross R theta. Okay, so if you do a dot product, so this will give you, so this will be the 0, 0, Z, so it's 6 cosine phi, right? Dot product, whatever you have here, right? So let me not repeat that, right? So whatever is here, you dot product here. So you dot product R phi cross R theta, right? So you just plug in here, right? Okay, so now the answer for here, this will be 216, right? So it's a 216 sine phi cosine squares phi. Okay, so sine phi cosine square phi. Okay, so cosine square phi here. Okay, so now finally I can find my integrations here, the s of f dot s. So I can rewrite it, all right, into this term. So I have a 216 sine phi cosine square phi. Then I do the d theta, d phi here. So the d theta, theta is from 0 to 2 pi. Then phi is from 0 to the pi over 2. So you see here, it turns out to be a pretty easy integration. So the final answers here, it will be what? The final answer is phi 1 to pi and over 3 is here. So for here, you know, if you say, hey, can I use the second formula? Yeah, you can do that. But then in here, then you will have the z squared is equal to the 36 minus x squared minus y squares, right? Then you need to take the square roots. And so you will say z is equal to the 36 minus x squared minus y squares, right? And then when you take the gx, gy, it doesn't, probably it's not going to simplify a lot. So the integration probably will be a little bit difficult. And then if you use the first method for the parameterization method, and this problem, the parameterization is not too bad because this is the sphere, right? So you know the spherical coordinates probably will be a good start, right? Okay, so let's take a look at the last ones here. So in here is the same thing. I'm going to, okay, evaluate this surface integration, and I have these functions here. Then the x here is the functions over the, okay, so here is x is a function over the z equal to xy. Okay, so the z equal to the xy is here, and the x is the region 0 to 1, y equal to the region 0 to 1. Okay, so this one's here, let's say here. All right, so this one, because I can find the graph of the function z equal, so I might be able to use the gx, gy method. And also the function is quite simple, so the partial derivative will probably looks good. Okay, so this is my p, this is my q, this is my r, right? Okay, then also my gxy is equal to the xy's, right? So the partial for x is y. Well, that looks very good. The partial for y is x here. All right. So now I can say the integration for the surface of this vector field over this surface is here. Okay, so let's take a look at the formula. Let me write down the formula here with rho p. So what is here? Rho z, rho x minus q. Then this is rho z, rho y plus r's, right? This is what our formula. Okay, so rho p, so p here, negative p, so it's negative x plus y plus z times rho z, rho x. Rho z, rho x is y. Then minus rho q, negative q, so it's negative x minus, so it's negative q, x minus y. Rho z, rho y is x here, right? Then plus r, r is what? R is 2xy, all right? So the r is, so the r is x, okay, so here, this one, be careful here. The r is xy plus z's, right? But z is equal to xy. So this is xy plus xy. So it's equal to the 2xy. So r is 2xy. Da-da, did you see here? You change everything to what? To the y and the x here, right? So you can say dx dy or dy dx. And they have a very good integration regions here. So you know, if you use this formula, you simplify it a lot. So this is 0, 1, 0, 1 here. All right. So you'll be able to just, simplify it or, combined. And then you kind of do the integration. So if you combine this one is 0, 1, then you can say this is a 2x1, you FOIL it, and then combine the similar terms, and the minus xy square minus x square dx dy. So the final integration is negative 1/3 here. All right. So these two examples, one is probably easier using parameterization method, and one is probably easier using the second formulas, right? So like we said, these formulas here also is pretty easy. Basically, you try to transfer all your variable back to x, y. The key things here, you do need to have like a function z is equal to some nice looking function of x, y. And so we'll make the gx, gy easier and for the integration purpose here. All right, that's it. And that is the surface integrations, right? So the second video, we talk about the surface integration over for the vector fields, right? In the first video, we talk about the scalar field. So the methodology basically is the same here, right? So you either use parallelizations or you can use the other method like in here. We can use the different way to do that. And the whole goal here is to try to simplify that integrations here. All right, so that's it. And we finished the surface integrals here. So our next topic, we're going to talk about the Stokes theorems here. That's another very interesting applications here. All right, that's it. Have a nice day. Looking forward to talk to you in our next video. Okay, bye.